So thank you very much for coming, everyone, today to the last Center for Math Medicine seminar of this academic year. Our speaker today is Masoud Ataei. I'm sorry.
It's Ataei, right?
Okay, Ataei. And from University of Toronto, Mississauga now.
Right.
And he's going to be speaking to us on theory of, again, Lehmer transforms and applications to biological signal processing. So thank you very much for coming.
Thank you, Kathleen, for the introduction. Good afternoon, everyone. It's a great pleasure to be here at the Fields Institute. Today, I will talk about, as mentioned, theory of Lehmer transform and its applications to biological signal processing. This is a topic at the intersection of signal processing, probability theory, and mathematical analysis. This is also a joint work with my colleague Steven Wang, who is present here. Our motivation comes from a recurring problem that we encountered when analyzing biological data. The classical time series approaches, no matter how refined, they often impose structural assumptions that the biological signals simply do not satisfy. So what we needed was a more intrinsic data adaptive approach, and the Lehmer transform arose as a response to that need. We named it a Lehmer transform after the number theorist Derek Lehmer, whose function is at the foundations of this new transformation. Today, I will walk through the core ideas behind Lehmer transform, its analytical and statistical properties, and its practical use. We will see that how this transform enables us to distinguish between healthy individuals and those suffering from major depressive disorder by analyzing their EEG signals. So the plan is that first, I will lay out the foundations of Lehmer transform, and then use it to construct a new family of distributions known as action potential distributions. And we will use these distributions to analyze the EEG signals for major depressive disorder. I will also go through several extensions that we were able to actually develop, and I will end with concluding remarks. Electroencephalography, or EEG, is a widely used tool in our modern neuroscience and clinical research. But analyzing EEG signals is challenging due to their complexity, non-stationarity, and susceptibility to noise. The traditional frequency-based approaches like Fourier and wavelet transforms have been extensively used in the area, but they struggle with various challenges when it comes to EEG signals. Basically, the EEG signals change very rapidly over time, making their analysis difficult for classical methods which assume stationarity. The Fourier transform assumes global periodicity, which makes it less effective when it comes to transient signals. And the wavelet transform, even though it provides a more localized analysis, but it depends on predefined basis functions, which might not always align well with the true characteristics of the data. More importantly, these methods require extensive pre-processing, such as artifact removal and segmentation, which can introduce subjectivity and potential loss of critical information. To address these challenges, we introduced the Lehmer transform, which summarizes, which is a statistical framework to summarize complex signals using moment-based representation. Unlike frequency-based methods, the Lehmer transform captures patterns directly from the data without assuming stationarity, which offers a more unified framework for signal processing. It provides a flexible, interpretable, and computationally efficient framework, which could be ideal for EEG analysis. Before delving into mathematical details, I would like to mention a few key challenges that we face in the area. The EEG signals contain various artifacts like eye blinks, muscle movements, and external interferences. The traditional noise filtering approach is highly subjective and usually assumes stationarity, which is rarely the case. The Lehmer transform eliminates the need for any pre-processing step. Also, many of the existing methods are mathematically involved, which makes the results relatively difficult to interpret, especially for those who might not be well equipped with mathematical tools, like practitioners in the area. The Lehmer transform provides a more tangible framework based on familiar statistical measures to interpret the results. The EEG datasets are also massive, usually exceeding terabytes of data. This makes real-world analysis very challenging for many of the methods. The Lehmer transform provides a computationally efficient approach, making real-time analysis possible. And also, there exists various temporal and spatial relations among different regions of the brain. But many of the existing methods treat these channels independently. The Lehmer transform retains essential temporal and spatial relationships which might exist among these channels, providing more reliable set of results. And finally, it is inevitable to deal with missing data when it comes to EEG analysis. These missing data come from electrode displacement and other artifacts. The current approach is imputation and interpolation of the time series, which can introduce bias. The Lehmer transform naturally handles the missing data without without making any artificial assumptions. Okay. Given a non-negative signal vector, the Lehmer transform is defined over the extended real line, and it maps the parameter S into a scalar summary statistic within the range from the minimum to maximum of the sample. Here, the core idea is that Lehmer transform is not a fixed statistic, like sample mean or maximum. Instead, it is a continuum of statistics. For each value of S, it computes a generalized ratio between S powers of the data. This creates a family of smooth aggregators that interpolate between classical summary measures. For instance, when S equals to 1, the numerator reduces to summation of observations, and denominator reduces to the sample size, returning the sample mean. As S goes to infinity, the transform converges to the maximum of the sample, and as it goes to negative infinity, it converges to the minimum of the sample. For the intermediate values of the S moment, one interpolates between these extremes. So instead of selecting a statistic upfront, we generate a whole continuum by sweeping across these suddency moments. This turns out to be highly useful when it comes to capturing both fine and coarse patterns from the data. The term suddency reflects how the transform responds to sudden changes in the signal. By tuning the parameter S, one can emphasize different aspects of the data. For instance, when S is small, one deals with statistics like harmonic mean, which dampen the impact of large values and are more robust to outliers. When S is large, one deals with statistics like contraharmonic mean, which amplify the dominant and high energy features, which these features can correspond to sudden spikes in the EEG activity. This transform turns out to be not only flexible, but also interpretable, providing a meaningful bridge between physical output and physiological interpretation. Now, let's examine the differentiability of the Lehmer transform, which reveals much about its inner mechanics. The first derivative, as shown in the double summation form here, captures an interesting interaction between three fundamental elements: differences, ratios, and nonlinear scaling. First, we have the additive difference term, which is a classic measure of dispersion in statistics. And it is particularly pronounced when we are dealing with highly variable data. Next, we have the log ratio between observations, which adds a multiplicative scaling variant factor. It captures relative contrast between observations, and unlike linear difference, it encodes directionality. Together, this combination forms a structure similar to measures from information geometry, such as Bergman divergence measures. The third term introduces a power-weighted influence where the value of the soudency moment modulates the influence put across the data spectrum. With S being greater than 1, the derivative puts more weight on larger values, prioritizing dominant features. But when S is small or less than 1, it shifts sensitivity towards smaller scale fluctuations. Together, this combination creates a powerful mechanism for how we adjust our understanding of the inner structure of the data. Basically, we can emphasize different aspects of the data by changing the parameter S here. Together, this form of the derivative, it seems to be very useful when it comes to constructing non-parametric distributions that I will cover in a bit. Yes.
I will ask a question. I certainly see some similarities and not with, say, Lejeune transform. Are there some convexity topics for this transform?
There is actually a convexity property I will cover. Yes, I will mention the convexity property.
In the last formula, for lambda double prime plus lambda prime squared. Yeah. Okay. So, lambda double prime minus lambda prime squared, actually, it's a common property, or it's a common property that emerges when you study large deviations like
I see. I see.
Not the same, but just this positive.
Yeah, thank you for the comment. So let me go through several properties of this transform. The Lehmer transform is an increasing function whose values always lie between the minimum and maximum of the sample. In case we have at least two distinct observations in the signal, then the Lehmer transform becomes strictly increasing. This provides an elegant justification for the classical inequalities between harmonic mean, geometric mean, and arithmetic mean. Another property is that Lehmer transform is homogeneous of degree 1, meaning that if we scale the inputs by a positive constant, the output gets scaled by the same constant. This has two significant implications. The first one is that it preserves the inner structure and relationship between the data. For instance, the relative magnitudes remain unchanged. The second one is that it responds to the changes in global scale, which could be particularly useful in EEG signals where the signals are measured in microvolts or millivolts. This ensures that the Lehmer transform remains sensitive to physical amplitude without requiring arbitrary normalization, which makes it possible to interpret the results in meaningful real-world units. And the last property is that Lehmer transform is short convex, meaning that if vector x majorizes vector y, or it is more dispersed than y, then it's going to have a higher value for the transform. This is also very useful when it comes to EEG applications, where different regions of the brain show different levels of variability. And in general, the data are heterogeneous. The short convexity reflects this heterogeneity. Now, let's move to the inverse of the transform. The inverse Lehmer transform takes in a statistic as input and outputs the solvency moment corresponding to it. This mapping is well defined within the range from minimum to maximum of the sample, where we assign positive infinity and negative infinity to the corresponding to the asymptotic behavior of the transform. Within the interior of the interval, we use the Lagrange-Berman expansion centered at a given solvency moment. The inverse transform enables us to backsolve for dynamic behavior of the signal by capturing solvency moments associated to observed statistics. This turns out to be very useful, especially in the context of biological signals, which enables us to infer results directly from the data, such as we can detect transient states or sudden spikes in EEG activation. Let's now explore the applications of inverse transform as applied to EEG signals. Here we see a raw EEG signal, a trace of changing voltages over time with clear patterns, with clear instances of neural variability, oscillatory patterns, and sporadic spikes. These are signatures.
Masoud, I was just wondering, so it's membrane like it's ear membrane, yeah? Or what membrane do you mean?
It's a
The ear membrane.
no, cell membranes in the brain.
Oh, I see. Okay, so that.
Yeah.
I understand. Yeah, which makes sense.
So these are the signatures of complex cortical dynamics during cognitive states. Here we see the inverse Lehmer transform applied to the signal. What is interesting to observe is emergence of a narrow band within which most of the solvency moments fall. This indicates that for most segments, the signal behaves regularly, and it is capturable by statistics close to the sample mean. But what is even more interesting are the points falling beyond this band, which can correspond to cognitive states, transient activation, and artifacts. Okay. Let's see how we can use the Lehmer transform to construct continuous probability distributions using discrete value deterministic signals. We consider a form of function where the Lehmer transform gets multiplied by e to the power of the transform. This function is non-decreasing and right continuous. And if we standardize the data between 0 and omega, where omega is the Lambert function evaluated at 1, then as s goes to negative infinity, the Lehmer transform approaches the minimum of the sample, which is 0, making the function f being equal to 0. As s goes to infinity, the Lehmer transform approaches maximum of the sample, which is omega, So the function f becomes omega multiplied by e to the power of omega, and using the Lambert function identities, this equals to 1. So this defines a distribution function. Yes, sure.
Masoud, quite a few people in this audience have probably never heard about Lambert W function, so you might want to say what it
Right.
is.
In the next slide, I'm going to actually briefly mention what the Lambert W function is. Yeah. So what we have satisfies three properties of distribution function. So f of s is a valid distribution function. And we can assign a real valued random variable s whose CDF coincides with this distribution function. We call this action potential distribution, or in short, APD. APD is a distribution over the solvency moments, and it assigns assigns probability over signal energy over the different solvency moments S. There's also an interesting relation between this CDF and the Lambert W function. So Lambert W function is defined as the inverse of the g of z equals to z e to the power of z. That's how we define the Lambert function. If we apply the W function to both sides of the CDF, on the right-hand side, we get W of L times e to the power of L, which returns L itself, or the Lehmer transform itself. So we get a very interesting identity that Lehmer transform at a specific solvency moment equals to the principal branch of the Lambert W function evaluated at the CDF of that particular solvency moment. This has various implications. The first one is that it enables us to find the inverse of the CDF in closed form using the Lambert W function. It is also analytically tractable, and one can find different properties of the distribution like moments, PDF, and entropy in closed form by using the properties of the Lambert function. The Lambert function itself arises in various areas of mathematics, such as delay differential equations, branching processes, and exponential growth processes. The presence of Lambert W function here hints at deeper structural parallels in neural propagation and memory effects in biological signals. Now, if we differentiate this CDF with respect to S, we get the probability density function, which is composed of three multiplicative elements. The exponential term dominates the behavior when S is large. This leads to exponential growth in the probability density, where the regions of high energy receive substantial probability mass. Next, when S is small, the Lehmer transform itself is small. Here, the function behaves almost linearly, ensuring a sort of logarithmic sensitivity. And this logarithmic sensitivity is useful in a sense that we deal with a smoother, more gradual density function, which can be more robust towards background noise. And finally, and perhaps most importantly, we have the derivative of the function, which plays the key role of adaptive modulator. The derivative of the function shows how the Lehmer transform itself is changing with respect to S. which can have a central role in shaping the distribution itself and determining how distribution is, whether distribution is sharply peaked or it is dispersed. The bottom line here is that APD is not just a fixed function. Rather, it is shaped by the data itself. Let's now generalize the non-parametric version of the action potential distribution by introducing two parameters, alpha and beta. This gives us a parametric family of action potential distributions. Here, alpha is a parameter between 0 and 1, and beta is greater than 1. This generalization provides more control over the distribution's shape, tail behavior, and sensitivity. The parameter alpha controls dispersion. If alpha is close to 0, then we get heavier tailed, more dispersed distribution. Whereas if alpha gets closer to 1, we get more concentrated distribution. The parameter beta corresponds to, is responsible for exponential scaling. And if it is very large, it emphasizes sudden spikes in the EEG signals. What we can observe here is that, yes?
Sorry, but I'm only question asker. So for beta responsible for the spikes, if we can go back to that electroencephalogram, please, and the one of the previous
absolutely.
slides. So so you mean no, the one actually just before, which this one. So you are speaking about these spikes, yeah?
Yeah, exactly. The spikes, exactly.
So when the inverse hits either negative or positive infinity.
Yeah, the inverse actually helps us to determine the spikes. Now, these spikes could be very actually subtle. Like we see a spike around 700 or 600, which shows the maximum of the signal. So this is recorded during the cognitive state for 10 minutes. And that one particular moment, that could be very, very interesting and very useful. It can carry very useful information. So these are the spikes that I'm talking about that are very rare. These are rare events that occur, but they occur from now and then.
And this is beautiful comment by Bova, that yes, there is beautiful mathematics here, and Lehmer and transform and everything, but this is CMM, so maybe every mathematical point that you make connect to this stuff.
For sure, for sure.
For example, how action potential is connected to the firing of the neuron.
Right, so yeah.
The other thing is the convexity that you mentioned before. Sorry, maybe I've missed it. It's very important in optimization, the convexity property. So how is it useful here in terms of the CMM subject matter?
Right. I will actually get to that part of applications in the third part of the talk. We will see the direct connection with brain and how we can interpret these results within the context of biological signal. First, I'm just going through the mathematical background here, tools that we develop, and then I will show the connections. This could actually clarify many, many points here. And also, what we did here is not just convexity, it is the short convexity, which appears in theory of majorization. So we talk about whether one vector majorizes another one. It is a relatively different form of convexity, but it has relation with the familiar notion of the convexity. Yeah. The form of the density function we see here also bears a strong resemblance to generalized extreme value distributions, which are used in extreme value theory. Just like GEV, it uses exponentials and power laws to control the tail behavior. It also has tunable parameters which govern the different behaviors of the distribution. It can also generate a wide range of distributions from thin-tailed to heavy-tailed distributions. So this resemblance, of course, this is the area that Vova is expert. There's a good resemblance with the generalized value distributions here. Generalized extreme value distributions. Okay, here we see the plots of action potential distributions by changing the values of alpha and beta. We fix the value of alpha at 1% and change the value of beta, and we see that different tail behaviors appear in these distributions with different levels of concentration. If we fix the value of alpha at 1 and change the values of beta, then even more different shapes of distributions appear where we see more concentrated distributions, having shapes close to bell shape. But also we get different tail behaviors. And finally, if we fix the value of alpha at very small number and change the values of beta, we get bell-shaped curves with different concentrations and tail behaviors. This shows that the action potential distribution, especially the parametric family that we introduced, can generate a wide range of distribution based on the underlying data. How we estimate these parameters could be through maximum likelihood estimation, but to best of our experience, fixing alpha at 1/2 and beta at 2, that is very suitable for analysis of EEG signals. It can capture the firings and the activation of the neurons. Let me start.
Sorry, I'm gonna have to
Yes,
ask a question.
absolutely.
Because I'm having a hard time connecting the distribution you just shown back to the EEG signal. So you take your EEG signal and you're going to do this transform, then you have S values, right? And then are you making a histogram of these?
No, we have the S values, and then we define this distribution over the S values. So this is a
But
distribution.
the S values come from the signal. So are you trying
The
to
S values
determine
come
alpha
from
and
the
beta?
Lehmer transform. The Lehmer transform depends on a parameter which we call the solvency moment. And then we use the Lehmer transform itself to construct a PDF, a density function. And this density function gives me the probabilities over different solvency moments. For instance, it tells me what are the chances that we observe sample mean in our data. What are the chances that some sample mean is the dominant statistic among all possible statistics within the range of the data from the minimum to maximum? It could be the maximum of the sample, which is the most representative statistic. And this probability tells me that which statistics within the range from minimum and maximum, which is going to be infinite number of statistics here. It's not even countable, uncountable, because we are generating a whole continuum. Which of these statistics is more probable? This is what the distribution tells me. For instance, in the case of the red PDF, it tells me a distribution having solvency moment close to, let's say, 10. That is most probable statistic. So if I'm going to choose one statistic to analyze the EEG signal, it is best if I choose a statistic corresponding to solvency moment 10, which is going to be larger than the sample mean. So this is a probability over these different solvency moments. It tells me how probable each of these solvency moments are based on the data. It could be that a data contains, it's just a regular data set, regular signal, EEG signal without spikes. In that case, we expect that sample mean could be a good representative as a statistic to capture the behavior of the data. And the probability density is going to put more weight on the sample mean instead of putting more weight on the maximum or minimum of the solvencies. Yes.
So just a comment, perhaps like if you have a toy example to show us in order for some members of the audience to digest the stuff
Right.
faster. Like a simple
Everyone just
EEG.
go through
Yeah,
at the end.
okay.
Yeah, at the end we can come back if it doesn't clarify.
Thank you.
Sure. So let me just briefly investigate the joint effect of alpha and beta. For small alpha and small beta, the distribution captures weak EEG responses and low amplitude fluctuations. For small alpha and large beta, it detects bursts and spikes in EEG activity, such as epileptic events. For large alpha and small beta, it is suitable for general EEG trend analysis with balanced fluctuations. And finally, for large alpha and large beta, it emphasizes dominant neural oscillations, which could be very useful for cognitive state monitoring. Now, we get to the application part and see how these are really used. The data set that we considered in this study contains 34 diagnosed subjects with major depressive disorder, 17 of whom are males and the other 17 are females. We also have 30 healthy controls which are used in the study. And our objective is to identify patterns in EEG recordings that can help us to distinguish between healthy controls and those diagnosed with major depressive disorder. We will analyze EEG signals across different experimental conditions. Also, these experiments have been conducted at Hospital University Sains, Malaysia. Each subject in the study underwent three experimental conditions. The first one was resting state with eyes closed, which captures more alpha waves in the brain. The second one was resting state with eyes closed, where the visual cortex becomes more active. And the last one was visual cognitive task, namely P300 task, performed during EEG recording. For eyes closed and eyes open, we had experiments lasting 5 minutes containing 77,000 signals per channel. And for the task, the duration was 10 minutes, leading to 155,000 signals per channel. These are massive data sets that we are dealing with. We recorded these signals over 19 channels, which were sampled at 256 hertz. One key challenge when dealing with EEG signals is how we handle the missing data. As I mentioned previously, many existing methods struggle with handling the missing data. The limit transform handles these missing data by something we call implicit imputation. So the missing values are inherently compensated by the weighted structure of the transform, where the transform adjusts dynamically by emphasizing available high energy components. Unlike interpolation, this does not introduce artificial distortions in the EEG signal. Also, when it comes to censored or truncated data, the limit transform is very powerful. It remains well defined even when EEG segments are partially missing. And it adapts to incomplete signals without requiring full time series reconstruction. The data set that we dealt with here contained almost 6% of missing data as shown in this table. And our methodology successfully managed these missing data. Okay. Let's go through the spatial organization of the electrodes on the skull. On the top, we have frontal cortex, which is responsible for executive function, attention, and cognitive flexibility. On the sides, we have temporal lobes, which are responsible for language and memory. Through the midline, we have the central and parietal lobes, which are responsible for sensory motor, readiness, and spatial processing. And towards the posterior, we have occipital lobes, which are responsible for visual processing. Now, let's see how these action potential distributions look like for healthy subject mapped on this 1020 international system for electrode placement. The pattern that we observe here is that most distributions have relatively high variability, and most of them are unimodal distributions.
Sorry, I have
Yes,
to
yes.
ask, how did you generate these plots? Because these are not the EEG signals, so you've just jumped now.
So for each EEG signal, we computed the action potential distribution, which is the f of s that we see here. So this is the density function that we generate for each of these EEG signals. And the plots are the plots corresponding to this density function. Alpha and beta, you can use maximum likelihood estimation, but a simple way would be to choose alpha to be 1/2 and beta to be 2. That turns out to be a very useful setting. So what happens here is that L of S, which is the limit transform, that deals with the signal itself. It takes in the signal and gives us an output for each value of S. And then we use this limit transform itself, which is based on data, to define the probability distributions.
The best result with Ataei. Sorry. I'm sorry. Thank you.
So you got the best result with alpha equals to 0.5 and beta equals to 2, right?
Yeah, exactly.
So what was the measure for detecting best results?
Well, based on how powerful our method turned out to discern the MDD subjects from healthy subjects, that's how we can judge whether that's a good setting or not. Of course, this is a good setting for major depressive disorder. If the application, for instance, is epileptic analysis, then we might end up with other setting, which could be optimal. But in general, in order to find this optimal value, we have a methodology which is maximum likelihood estimation. So we can use that. Using maximum likelihood estimation for the data sets that we have here, for almost all channels, we get values close to 1/2 and 2 for alpha and beta. That's why we can fix the values here.
Can you clarify, but if you were going to use maximum likelihood estimation, you have to have a data set that you're fitting to, but you don't know alpha and beta.
Right,
So-
but we have the data set.
You have the signal data set. You don't have the distribution data set. And you're,
We have the distribution.
how do you create the distribution data set?
To create a distribution, we take the limit transform of this signal. Then the limit transform maps something we call solvency moment to probability values. So it is based on the signal itself. But the distribution doesn't deal with the signal. It is not defined over the signal. It is defined over the solvency moments.
bit.
Yeah.
I think what Masoud is trying to say is that, well, once you have the signal, and that's observation, that have nothing to do with the definition of the PDF or right here. And then you try to match them. So it's like traditional statistical inference. You have observations, you have the likelihood functions. You try to choose the best alpha and beta to maximize your likelihood function.
If I just can make a comment, yeah, so you basically have the original EEG, it's like a time series, yeah? So then we implement Lehmer transform, and then once we deal with the transform, we introduce a certain artificial probability distribution for a Lehmer transform. That's
Exactly.
basically what happens. So Lehmer transform is a kind of link between the original time series, EEG, and the artificial probability distribution. So once we got this artificial probability distribution, we are capable to employ the methods of probability theory. So the Lambert function, of course, is great to have. So the variety of these histograms, it just shows how rich our model is, but it's like a third step. So these are artificial distributions.
Exactly. These are secondary distributions that we are generating. It's not exactly based on the signal itself. Thank you, Vova, for the clarification, and thank you. Yeah. Yes, John.
Very quick, sorry.
No rush.
So I'm trying to connect these. So I'm not expert enough in this field. I'm trying to connect these items to my basic knowledge. So what are the numbers on the horizontal line?
These are the solvency moments. On the horizontal line,
Is
we
it
have solvency
time?
moments going from negative infinity to infinity.
Is it time or?
No, these are solvency moments. What does it
Okay.
mean? Negative infinity means that we are dealing with minimum of the sample. Positive infinity deals with the maximum of the sample. Or intermediate values interpolate between these extremes. For instance, for s equals to 1, we are dealing with sample mean. For s equals to 0, we are dealing with harmonic mean. This is a probability distribution that tells me which of these statistics are more probable and more appropriate. So the horizontal line is the solvency moment, and the vertical shows the probability density of the action potential distribution. So these are the plots for healthy distribution, healthy subject, and it shows regulated activity in the brain. But when we compare it to plots of action potential distribution for MDD subject, we see different patterns. So these are for the healthy subject, which are very variable and usually unimodal distributions, meaning that statistics like sample mean are sufficient to capture the information about the signals because of normal excitations in the neural firings. This is the meaning of unimodal. It means that certain statistics can work very well because there's a normal, well-regulated activation in the neurons. But when it comes to MDD subject, we see unimodal distributions. We see bimodal, distributions. Bimodal distributions, it means that there's not a regulated activity in the brain. In other words, the firing, excitations, and resting states happen in extreme ways. They are not well regulated. But perhaps it's most useful if we consider the heat map of these distributions. This is the heat map of differential entropies computed for each of the distributions. So we have 19 distributions here. For each of these 19 distributions, we compute the differential entropy. which measures the information contained within that distribution. The heat maps we see here, the warmer colors show higher activity or higher entropy, and cooler colors show low complexity regions. Let's first focus on the heat map of the healthy individual on the left-hand side. The channels FZ and F3 on the top, which correspond to midline and left frontal cortex, have relatively high values of entropy. These regions are central for executive function, attention, and cognitive flexibility, which are crucial for performing mental tasks. So one should consider that the EEG signals we are comparing here are for the subjects when performing a visual task. So we expect that the visual lobes of the brain should be active, and thus together with other parts related to analysis and perception. In the occipital lobes, we have O1 and O2, where both of them are highly active, having relatively large values of entropy. This indicates a strong visual engagement and responsiveness to stimuli. Moving to central and parietal lobes, such as CZ, C3, PZ, and P3, we see a modest level of entropies. This indicates a stable sensory motor readiness and spatial processing. Now, moving to the heat map of the MDD subject on the right-hand side, we see a striking observation where the frontal cortex is asymmetric. FP2, F4, and F8 on the top, they show abnormally high entropy values as compared to their counterparts in FZ, F3, and F7. This suggests suppression in the left frontal cortex, which is linked to emotional withdrawal and motivational deficit in major depressive disorder. C3 in the left motor has the lowest entropy value in the entire map. This indicates reduced dynamical variability in the motor circuits, which is consistent with psychomotor slowing, which is also a hallmark symptom of major depressive disorder. Moving posteriorly, we have O2 and PZ, which are muted. This indicates reduced sensory engagement and blunted visual responsiveness. So this is how these distributions can be interpreted. First, using the signal, we define the Lehmer transform. Then the Lehmer transform leads to the probability distribution, which we call it action potential distribution. Then for each of these action potential distributions, we compute the differential entropies, and such a heat maps can reveal much about the inner brain structure in major depressive subjects and those who are healthy. Now, we gain some insight about.
Sorry, I have a
Yes,
question.
yes,
New
absolutely.
factor, you can't go through a slide without a question.
Yeah, absolutely.
So, I don't know what it means differential entropy. You can calculate the entropy from the distribute probability. What does differential entropy mean?
Right. For any distribution, the differential entropy is defined as the PDF multiplied by log of PDF. So that's how we define the
That's entropy,
that's
right?
entropy.
Yes. What's
which we call it
differential?
It's called differential entropy. So the entropy itself,
Oh, so it's just the entropy.
the entropy itself is defined for the
Oh, if it's a probability,
it is defined for
Oh,
the
okay.
discrete case.
I see, okay.
Ge-
It's the
Its
continuous.
generalization to the
Okay.
continuous setting is called differential entropy.
Okay, I didn't know that, sorry.
Yeah.
Second question is, how significant are the differences? Like, because when I look at this, I think the difference between 32 and 40 is not very big. And maybe this is just noise because you're only comparing two different patients. Right? So how significant is the difference between 32 and 40?
It turns out it is actually quite significant.
Okay,
Because
Did-
it
did you ha-
captures the curvature of the density functions, and even small values, small differences that can actually show different behaviors of the distribution.
so did you look at the population of seven, whatever, however many were MDD versus normal? Like these are just one
This
patient.
is
The
on
N
the one
equals one,
subject during the task.
So do you have the where you showed that this pattern is consistent across your population?
Yeah, we find actually consistent patterns. Of course, I don't have the graphs for more than one subject, but this observation, how effective it is to interpret the results in this way, reflects itself when we develop machine learning algorithms. Because machine learning algorithms are going to be based on the same insight. So for each of the subjects, we do feature extraction by defining 5 quantities. The first 3 quantities are entropy-like measures, which basically measure the concentration of information before, between, and after 2 modal points. And the 2 remaining measures are the CDF and complementary CDF at these 2 modals. The first mode, the first modal point, which is M1, is defined as the mode of the distribution before S equals to 1. This S equals to 1 means it corresponds to the sample mean. And the M2 is defined as the mode of the distribution when S is greater than 1, which is, again corresponds to the sample mean. So in a sense, we want to capture the bimodal behavior of these MDD patients as compared to the unimodal behavior of the healthy individuals. This is a consistent pattern that we observe among all patients. All patients, MDD patients, they have bimodal distributions, whereas when it comes to healthy ones, they're usually unimodal and they have wide variability. And this wide variability reflects itself in the differential entropy. So even small changes in the differential entropy, it tells me how concentrated a distribution is. Like the second ones are more concentrated as the distributions we see here.
Your bimodal looks like very weakly bimodal. There is only small blip. I don't know if you have some comment about it.
Yeah, exactly.
Secondly, the controls you had 17 and 17 healthy, male, females, but the MDD, you didn't tell me how many females, how many males, and it's very important to distinguish.
Right. Regarding the, so it was for MDD that we had 17 males and 17 females. Yeah, regarding the healthy subjects, I myself don't have the information. The information have not been released by the researchers who have provided the data set. So I do not have access to those information. But I'm guessing that there's going to be a balance between females and males. But yeah, the question that you asked is actually great, that we have bimodal distributions, but it seems that one of the modes is very weak. But that weak mode, it tells me that how the neurons are acting in the resting state. It tells me that there are 2 extreme behaviors. Either they are really at the resting state, or they are very excited. There's nothing in between. There's no dynamics. So that weak mode, it tells me that lower solvency moments appear to be very probable. So most of the neurons are basically suppressed. They are either suppressed or they are very active. They are excited. Whereas in the healthy individual, we don't have such a suppression behavior. Rather, it is a dynamics between resting state and excitation. I hope that clarifies.
Means that the MDD is only very, very small. It's a very, very small leap, right? That bimodal is very weak. But that's already enough to tell me about unhealthy.
Exactly.
It's very interesting.
So it's just been pointed out we're at time. So I'm going to say no more questions from the audience. We're just going to let you finish. Hopefully you can finish in 5 minutes.
Okay.
Okay.
For sure. So we trained classifiers based on machine learning approaches using these extracted features. We considered 3 classifiers: the Gaussian naive Bayes, which is simple yet effective, convolutional neural networks using encoder-decoder architecture, and bootstrap aggregated decision trees, which are known to be which are known for their robustness and interpretability. Our evaluation metrics were accuracy, which gives the overall classification correction, sensitivity, which tells me the ability to detect MDD subjects, and specificity, which shows the ability to correctly classify healthy subjects. The Gaussian naive Bayes combined with Lehmer-based features achieved the overall best accuracy of 94% with a balanced sensitivity and specificity. The convolutional neural networks achieved a very impressive specificity, but it had relatively low sensitivity. And finally, the bootstrap aggregated decision tree combined with Lehmer-based features achieved the highest sensitivity of 94%, but with a slightly low specificity. These observations show that our proposed methodology to extract features has been very effective across different classifiers, and it shows, in a sense, the success of our methodology. In order to gain an understanding of how good this accuracy is, we can compare our model with previously developed methodologies. You can see the accuracies in the first column. We have methods like PST ratios, ATR index, and coherence measures, 2 recent wavelet transform-based methodologies. The Lehmer transform outperforms all the previously developed methods by a relatively large margin. The only competitive approach remains the wavelet transform, which has recently been proposed. This indicates that our methodology to define the Lehmer transform and thereafter the action potential distributions and using them to extract features has been very successful.
No questions until the end, sorry. You were just going to let him finish and then we'll quit.
Okay. So what we did was we proposed the Lehmer transform framework, which unifies is a unified statistical framework for analyzing complex non-stationary signals. This bridges classical statistics and signal processing by generalizing means using a continuous moment-based representation. And we also investigated different applications of different applications to EEG analysis and shows that this methodology is powerful to discern MDD subjects from healthy individuals. In the future, it is useful to integrate this framework with deep learning architectures and see where that leads, because in our recent research, we came up with new architecture of neural networks using Lehmer activation units. And it seems that this Lehmer transform has implications to artificial intelligence area. It's also useful to consider applications to other modalities like fMRI, EEG, and multimodal fusion. Thank you very much for your attention. Thank you.
Okay, thank you very much. It was very active, so I'm sure there's more questions. Bova?
What, yeah, Masoud, you just showed a relation with zeta function. But I just saw.
Yeah, yeah.
Can you show that slide? Which you
Absolutely.
didn't show,
This is actually a
please?
very interesting relationship.
Mhm.
If we consider the harmonic sequence,
Mhm.
which is defined by 1/n, then the Lehmer transform applied to this harmonic sequence gives us zeta of s in the numerator and zeta of s minus 1 in denominator. On the other hand, if I consider my sequence of observations to be the natural numbers, then the numerator of the Lehmer transform is going to be the zeta at negative s divided by zeta at 1 minus s. If we consider a change of variables, 1 minus s for s in the second form, the numerator becomes zeta of s minus 1 and denominator becomes zeta of s. And we get very interesting identity that Lehmer transform applied to harmonic sequence gives us 1 divided by Lehmer transform applied to natural numbers evaluated at 1 minus s. This is an involution relation, and it can have potential implications to analytic continuation of the zeta function.
Thank you, Masoud.
Yeah, sure.
It's a beautiful mathematical connection here, because the pole at s equal 1 is common to the beginning and the end.
Exactly,
So
exactly.
It's a beautiful thing. I have another comment which may be useful for everybody here. Ramurthy gave us super talk. He's a number theorist. He gave a super talk in a workshop that I'm in, and he mentioned Lehmer as one of his mathematical genealogy. So Lehmer, you demonstrated that Lehmer is a powerful mathematician.
It's interesting. Thank you for the comment.
I enjoyed it. So I'm in and out.
Thanks so much.
Okay, any other questions? Do you have a question? Okay. All right, well, thank you very much again, Masoud.
Thank you.